Okay, today we're going to talk about prime factorization. It's something that we need to know how to do in order to be successful at simplifying radical roots that are not perfect squares or perfect cubes or perfect fourth numbers, etc. So we're going to be looking at slide 76 in your math interactive digital notebook, as well as entering some notes in your paper notebook. So let's go to that. Your TOC is going to be review of prime factorization, 76, 77 slides, and page 15 of notes. So hopefully you covered what prime numbers were in sixth grade and what composite numbers were. But we're going to review them and just talk about that real quick. So after you write this down, we're going to go to page 15 in your notebook. So prime factorization review. First thing we need to know is what is a prime number. And hopefully, you know that prime means special, means unique. And in this case, a prime number is a number that is only evenly divisible. And what we mean by evenly divisible is that when you divide by this number, you have no remainder. By two factors, and the factors are going to be 1 and the number. So an example of this would be 17. The only numbers that go evenly into 17 would be 1 and 17. 1 goes into 17 17 times, and 17 goes into 17 one time. We also sometimes call this a factor pair, okay? And a number that's prime is only going to have one set of factor pairs. And those factor pair is also going to be its prime factorization. The opposite of a prime number is a composite number. And it's a number with more than two factors. So the number 12 is composite. Why? Because it has factors of 2. 2 can go into 12 evenly. 3, 4, 6, 12, and of course the number 1. So if we looked at the factor pairs, 1 and 12 would be a factor pair, 2 and 6, and 3 and 4. Now its prime factorization is something different, okay? Because with prime factorization, you're looking to find out what expression of primes, when multiplied together, will give you the original number. So for example, when I said this is its prime factorization, 1 times 17 is 17. 1 times 2 times 3 times 4 times 6 times 12 is not going to give us the number 12. And so in order to find what that prime factorization is, we prime factor. And there are two methods that we usually use to do that. But first, let's write down what prime factorization is so we remember. Prime factorization so it's an expression of prime numbers that when multiplied the product, remember the product is the answer to a multiplication problem, equals the original number. Okay. And there's two methods to be able to do this. One are factor trees. Okay. And that's what you learned about in 6th grade. You learned how to do a factor tree, where you would say, well, 36. Well, 36 can be 6 times 6, and the 6's can be 2 times 3, and 2 times 3. So essentially, when you're factor treeing, there are no rules in terms of which factor pair you're going to use as your first breakdown. And while it's valid, we want to use a particular method that's going to help us see if a number has duplicate factors in it, so that we know if it can be taken out of the radical sign, right? Because we're looking to simplify radicals that may or may not be perfect numbers. Most often we're going to use this for non-perfect square numbers, non-perfect cubed numbers. So the second method we can use is called the upside down birthday cake. And with a birthday cake, of course, we always need to have a candle. And that's what our goal is. The number that we're factoring is going to be on top, and the bottom should be its birthday candle. So if I'm looking at 36, 36 is divisible by 2. And 36 divided by 2 is 18, right? If I keep on going, 18 is divisible by 2, and 18 divided by 2 is 9, and 9 is divisible by 3, goes into 9 3 times, 3, and then 1. So the prime factorization for 36, we could write that as 2 times 2 times 3 times 3, or we'd write it as 2 squared times 3 squared. Okay? And that's what we're going to want to get to, because we're going to use that when we simplify non-perfect square numbers. So what are the other tools that we need? Well, we need to definitely be able to look at and know what are the prime numbers, because the rules say that always start with the smallest prime. That goes into the number. Right? That's where we want to start. And use that prime number until it no longer divides evenly. Into the number on the cake layer. Okay. And that's what we did. This is layer. That's what we did up here. So 36 is an even number, and it's divisible by 2, the smallest prime that goes into it. And 18 is divisible by 2. So I'm continuing to use that same prime number until it doesn't work anymore, because 2 wouldn't go into 9. But then 3 did, so that's how I would continue on. So I have to know what the prime numbers are. I should know them in order. So this is where we want to look at a hundreds chart, just to kind of, in no way are going to give us all of them, but kind of give us a start. And there's a hundreds chart. I put a hundreds chart in your digital interactive notebook. So 1 is not a prime number. Why? Because it doesn't fit the definition. To be a prime number, you have to have 2 factors, 1 and yourself. 1 only has 1, because 1 is itself. So we don't really count that as a prime, because of course any number divided by 1 is itself. So it's not helping us break it down. And that's what we're looking for. We're looking to break down a number into its prime factorization. 2 is the only even prime number, because any even number beyond 2 is always divisible by 2. 3, 5. 4 is not, because it's divisible by 1, 2, and 4. 6 is not, because it's divisible by 1, 2, 3, and 6. 7 is. 8 is not, because it's divisible by 1, 2, 4, and 8. 9 is not, because it's divisible by 1, 3, and 9. 10 is not, because it's divisible by 1, 2, 5, and 10. 11 is, because it's only divisible by 1 and 11. 13, 12 is not, it's divisible by at least 1, 2, 12. So even if I don't know all the factors, if I know if it's another, has an additional one, it will not be. So in other words, all of these even numbers will not be prime numbers because they're divisible by 2. So you really want to concentrate on the odds. 15, not, because it's divisible by 5, besides 1 and 15. 17, yes. 19, yes. 21, no. So in fact, I could just go down the rows like this and see if it's divisible by something else. So this is where you'd want to use the divisibility rules that you learned as well. And we know any number that's even is divisible by 2. We know any number that ends in a 5 or a 0 is divisible by 5. So those wouldn't be prime, those would be composite. We should know any number under 100 that is double, like 22, 33, 44 are divisible by 11. Another divisibility rule is when you add the digits, so 2 plus 1. 2 plus 1 is 3. 3 is divisible by 3, therefore the whole number is divisible by 3. So something like 75. Yes, it's divisible by 5, but 7 plus 5 is 12, so that would also be divisible by 3. So you're going to want to go through and highlight just the prime numbers, because when we go to do birthday cake, we're going to want to start with the smallest prime that goes into it, and that's what we're going to have to think about. Yeah. So some other examples of birthday cake. Let's do a big one. Let's do 108. So I know 108 is even. So 2 goes into 108, 2 goes into 150, 2 goes into 8, 4, so 54. 4 is an even number, so 2 can go in. 2 goes into 50, 25. 2 goes into 4 twice, so 27. 27 is an odd number. 2 is not going to go into it. Will 3. 2 plus 7 is 9. 9 is divisible by 3. So 3 goes in 9 times. 3, 3, 3, and finally my candle. So I can see this prime factorization is 2 times 2 times 3 times 3 times 3. Or because I know how to write in exponents, I can just say 2 to the second times 3 to the third. Okay. And that is how you're going to do prime factorization of the numbers in GP2.